I can't see this. So if you couldn't see that other chart, here's the problem. So again, the conclusion is, if you want the ratio of safe to poison to be 10 to the third to 1, okay, you want the pH to be 9.92. Okay, you ready for problem number 3? Problem number 3 goes like this. Joe Chemist is kind of a gambler, and so he's wondering, if I wanted to have a 50-50 mixture of poison versus safe, what would I adjust the pH to? Okay, so here's the problem. What is the pH when you have a 50-50 mixture? In other words, the H2S equals the HS minus. Okay, again, we're dealing with the same chemical system. Again, we're talking about equilibrium. So here's the mass action expression. The K sub A is equal to products of reactants. Now notice how nice the math is. If they're equal to each other, they cancel out. I'm going to use this. They cancel out. And da-da-da-da. Notice the hydrogen ion concentration equals the K sub A. Converting hydrogen to pH, you get 6.92. So if Joe Chemist wants a 50-50 mixture, the pH has to be 6.92. Okay, questions on it? Okay, so let me hold the chart for those of you that couldn't see this. Okay, so we want a 50-50 mixture of the poison and the safe form. So here's the chemical system we're dealing with. You write the mass action expression, and notice if it's a 50-50 mixture, if they're equal, these cancel out, and that makes it really nice. Hydrogen concentration equals the K sub A, and therefore pH equals minus log of that, which would be 6.92. Now, if you didn't get these answers, please copy them down, because I'm now going to show you another method of getting these 3 answers. Okay.
Can you lift that up, Professor? Because we can't see the bottom one.
You can't see the bottom one. So if I go like that, is that better or worse?
Other way, yeah.
Okay. Better?
We're still missing the bottom one.
Okay. So,
that's good. Thank you.
Okay. Now, the method I'm going to teach you now for all these problems is called the table method. And it's going to be a very important part of the course. Abby, I'm just wondering, are you able to see the chat files?
Yes.
Oh, good. Okay, the table method.
Professor?
Yes.
How are you getting the pHs again?
Minus the log of the hydrogen ion concentration. Should I go back to the last one?
Yeah.
Okay, I'll go back to the last one. Let me get this out of the way for a moment. Okay, so looking at the last one, Jessica, are you able to see that okay?
Yeah.
Okay, so you're asking how I'm getting the pHs. Okay, if you get the hydrogen ion concentration, pH, remember, is minus the log of the hydrogen concentration. So in your calculator, if you take minus the log of 1.2 times 10 minus 7, this is what you should get on your calculator.
Oh, from 14.
That bring back pleasant memories to you?
Yeah. Okay.
Are you okay then?
Yeah.
Because you're asking the right question, so I'm glad you asked it. Okay, everybody okay? So how do you get pH again? If you know the hydrogen concentration equilibrium, take minus the log of it on your calculator, and that'll give you the pH. Okay. You're about to see one of my favorite parts of the course, the table method. Okay, so let me find it here. By the way, Jessica, are you able to see the charts? Are you able to see this right now when I put it up? I'm just curious if it works for you.
Yeah, it's working. I just have to download it.
Okay, so here's how the table method works. In general, when you have a weak acid, here is the mass action expression. So the constant is equal to products over reactants. Now, what happens when the concentration of the acid is equal to the concentration of the conjugate base? In other words, when you have a 50-50 mixture, Guy, the math is great. They cancel out, and so the K sub A is equal to the hydrogen concentration. Let me say it once more. Look at the mass action expression. When the acid and conjugate base are equal, they cancel out, and then the K sub A equals hydrogen concentration. This is just a great revelation. People decide to do this. Take minus the log of both sides. Can you guys see the yellow, by the way? When I do that?
No.
Yes or no?
No.
No.
I'm wasting my time. Okay. So when you take minus the log of both sides, you get this. Minus the log of the hydrogen concentration is pH. And here's a new term for you. Minus the log of K sub A is called pK sub A. pK sub A is so important. Some textbooks don't even bother giving you K sub A. They just give you pK sub A. So what does lowercase p mean in science? It means minus the log of something. Okay, for those that can't see that, let me show you the chart. This is good for some of you to get a double dose of this. That's good. Okay, so here's a general equilibrium expression. What happens when the acid and base are equal to each other? They cancel out, and the K sub A equals the hydrogen concentration. Now, if you take minus log of both sides, minus log of hydrogen is pH. Minus log of K sub A is called pK sub A. So this is kind of the basis of the table method. You're not done with the table method yet, but this is the start of looking how it goes. Now, when you first learn about the table method, what you want to do is you want to get 4 rows. So let me show you what I mean by the 4 rows. You see all this chart okay? Okay, now I'm going back to our particular problem where the K sub A was given as 1.2 times minus 7. Now, if you take the minus of log of that on your calculator, you get a pK sub A of 6.92. Now, when you first start the table method, you want to have 4 rows. Hydrogen concentration, pH, ratio of base to acid, and acid to base. Now, you always start the table method by purposely making the pH equal to pK sub A. So if the pK sub A is 6.92, you purposely start at a pH of 6.92. Why? Because when the pH equals to pK sub A, the ratio of base to acid and acid to base is 1 to 1. So you always know that as your starting point. Also on the chart, notice that I've converted pH to hydrogen concentration. So 6.92 means the hydrogen concentration is 1.2 times 10 minus 7. So if you're taking notes on this, why don't you copy that middle part first? Copy down the pH being 6.92, ratio of both are 1 to 1, and the hydrogen concentration of 1.2 times minus 7. I'll give you a moment to copy that down or digest it before I go on. Now look on this chart and see what happens when we purposely make the pH 1 number higher, go to 7.92. look at what the pH is at 7.92. It's 1.2 times 10 to minus 8. Okay, so if you're not sure, you can do that in your calculator. Remember how to go from pH to hydrogen concentration? Hydrogen concentration is 10 to the minus pH, which would be 1.2 times minus 8. Now compare how the hydrogen concentrations change. As you go to 1 pH unit higher, it changes by a power of 10. It kind of makes sense because pH is a log scale. Now, notice how the ratio of base to acid has changed. If you go from 1 pH unit higher, then the ratio changes by a factor of 10. So notice the base to acid is 10 to 1. If you look at the bottom part, the acid to base is 1 to 10. Now, if you believe in trends, what happens if you go to 5.92? Again, the ratio changes by a factor of 10, but now notice it's the base to acid is 1 to 10, and the acid to base is 10 to 1. Okay. If you can't see this chart, let me put it up. Okay, let me talk you this through again. Okay, so on this chart, you always purposely start with the pH equal to pK sub A. What's the pK sub A again? It's minus the log of the K sub A. So in this case, the pK sub A is 6.92. Okay, and so the beauty of having the pH equal to pK sub A is you know the ratios. They're 1 to 1. That's what I proved to you before. Now here's the new information. If you go 1 pH unit higher, the ratio changes by a factor of 10. So now you have 10 base to 1 acid, or reversing it around 1 acid, 10 base. And the same thing is true if you go in this direction. As you make the pH unit more acidic by 1 unit, the ratio changes 10 acid to 1 base, or 10 base to 1 acid. Now, I want to prove this particular part to you, because you don't want to just take Berg's word for it. I want to prove to you. So here's the proof of how the table method works.